All right, so 4.01 dilations and similarity. First thing is just review some of the definitions we've talked about already. Lately, we've talked a lot about transformations. Well, dilation is a type of transformation. It's just different. Some of these definitions can go with more than one word, but for each word, we're going to choose the best answer. So I usually go by definitions first. So we have the movement of a figure from one location to another without a change in shape, size, or orientation. All right, well, that can go for reflection, rotation, and translation. So I'm just going to kind of skip that definition for right now. We have a transformation where the mirror image of a figure is shown directly opposite its line of reflection. All right, which one does that most closely match? Reflection, right? Mirror image probably told you, also line of reflection probably told you. So that's really specific to reflection. Yeah, the first one could also go with reflection, but you know, the second one's better. Transforms an object by making it larger or smaller. All right, it has to be dilation. You probably remember it from last year, but even if we haven't officially covered it in here yet, these other ones do not make things larger or smaller. So by process of elimination, it has to be dilation. Down here, we have a transformation in which a figure turns around a fixed point. Rotation, good. Turns around a fixed point. That's probably the indicator. And then translation would be this top one, right? So movement of a figure from one location to another. That's probably the biggest indicator for that one. Questions? All right, so now let's formally introduce dilation. Those transform an object by making it larger or smaller. When you increase a pre-image to create a larger image, that type of dilation is called an enlargement. Whereas if you decrease the pre-image to create a similar image, the dilation is called a reduction. All right, so larger or smaller. Characteristics of dilation. So in the previous transformations that we've learned, like translations, reflections, and rotations, we learned that the side lengths and angle measures remain constant, and that collinearity and betweenness of points is preserved. All right, so that's with the translations, reflections, and rotations. Right, where side lengths and angle measures are the same, collinearity is preserved. All right, but in a dilation, like we said, things get larger or smaller, but we're also trying to see, does it still have collinearity? Does it still have betweenness of points? So we'll see that next. All right, we're going to kind of discover it by looking at these images that were dilated. All right, so study the following images to discover relationships between side lengths, angle measures, and points in both triangles. So for side lengths, it may or may not be easy to see. We've kind of talked about it with similar figures before. But side lengths of two figures, like where one of them was dilated into the other, you should note that it changes by a scale factor. So if I said the blue triangle was dilated into the red triangle, well, that means that I multiply the same number to each side to get the other triangle. And that number should be the same number all around. And you can kind of see that like if I do each corresponding side over each other, because the scale factor is like a fraction. So if I do 2 over 3.5, so I'm doing this over this for that corresponding side. When I put that in my calculator, I get a decimal that if I round it is about 0.57. All right, if I do the same with all the other sides, like keep the corresponding sides together, so I have 3.9 divided by 6.8. I get the same decimal. Actually, it's off by 0.01, but you get the picture. All right, they probably just rounded a little differently when they were making their pictures. All right, but if I do that for each corresponding side, I get the same decimal all around. I think I actually put these two. But they should be the same or really close. Like the only difference would be how they decided to round it. All right, so dilated figures change by a scale factor. Now look at the next part in the middle for the angles. We'll probably look at it on your paper. I'm just saying, scroll down here so you don't. All right, but if you look for the angle measures of both triangles, what do you notice? Are they different? Are they the same? All right, they're the same all around. None of them are different. So they are identical or congruent, you could say. All right, so dilated figures still have the same angle measures. Betweenness of points, so what does that mean? Well, if E is between B and C in the pre-image, is it still between B and C in the dilated image? Yes. So we could say that the betweenness is preserved. That's the word they like to use. All right, so collinearity and betweenness are preserved in dilated images. Questions? All right, for this next slide, I'll kind of give you a hint where you should underline or highlight. So a little bit more about dilations. We have the angle measures of the pre-image and image after dilation do not change. This is what we noticed in the last slide. Also, we noticed that if, for example, point B lies on a B in the pre-image, then D prime should lie between A prime and B prime in the other image. So collinearity and betweenness of points is preserved. All right, if we name the first triangle or shape, whatever it is, in a counterclockwise direction, then the dilated image will also be named in that same direction. So if it's ABC, it'll be A prime, B prime, C prime. So that means the orientation does not change in a dilation. Now, the lengths we notice are the same or different? Try again. The side lengths. The side lengths did change. However, they changed by what's called a scale factor. So let me show you what's important here. All right, in a dilation, the pre-image is enlarged or reduced to create an image. Therefore, the lengths of each side will change. However, the corresponding sides are proportional to one another. So that's what that ratio that we kind of set up in the last slide, where they all equal the same thing, that's our scale factor, is what they equal. All right, questions? All right, the next chart is basically just showing you a summary of how in a translation, side length is the same, angle measure is the same, collinearity is preserved. That's the same for reflections and rotations too. But in dilation, you see it's different because scale factor changes. The other things are the same as before, but that's like the main thing. Questions? So before, when we were doing these three types of transformations, rotation, reflection, and translation, notice that they all made congruent images. But in dilations, they're not congruent, but they are similar. All right, so now let's do some examples where like math is involved. So we have an example of a dilation. We have trapezoid dial is dilated to trapezoid B prime, I prime, A prime, and so on. And it's shown here on the coordinate plane. If the center of dilation is at the origin, so the origin is where on the graph? At 0, 0, so where I'm putting that red mark, origin. What scale factor was trapezoid dial dilated? All right, so one thing that you'll have to write down, because it's not typed up for you, but you do need to know, is that when center of dilation, so when center of dilation is at the origin, or it'll usually tell you in the problem, when center of dilation is at the origin, we use the rule xy to kx comma ky, where k is the scale factor. All right. So that's our rule. And what essentially is happening is for each x and y value of our pre-image, we're multiplying it by something, which is our scale factor, which is k, to get our new coordinate. All right, so to figure out what scale factor, we are going to just pick one or two of the points. Like let's pick point D from the pre-image. So what's the coordinate of point D? Sorry if you're still reading. All right, but the coordinate of point B is -3, 6. And we don't know what k is yet, but we know that D primed is what coordinate? -1, 2. So in between, we multiplied something by both of these numbers in order to get -1, 2. Question so far? To figure out what number we multiplied by or what our scale factor is, we can kind of set it up as a algebra problem, right? So I have k times x, so x is -3, k we don't know, that's what we're solving for. -3 times k ended up equaling -1. Well, I can do some inverse operations to isolate the k. So what's opposite of multiplying by -3? So I'm going to divide by -3. And then what I do on one side, I have to do to the other side. So my k value, I have -1 over -3. Do you guys know what happens to that double negative? Becomes positive. So my k value is 1/3. All right, and that's what it asks for, is what's the scale factor. So really I could kind of circle this and be done. All right, but just to show you, we'll test it out with the y coordinate. So I have 6 times k ended up equaling 2. So do the inverse operations. Opposite of multiplying by 6 is dividing by 6. So do that on each side. We get k equals 2 over 6, which simplifies to what? 1/3. All right. So your simplified fraction, or if it's a whole number, that's fine too, is your scale factor. Questions? All right, so once you've finished writing that one down, we'll go ahead and start the break. So 15 minutes. We'll be back at 12:26. We have Lizzie is making some clothes based off patterns she designed. One piece of that pattern is shown on the coordinate plane. Her older sister Jackie has asked her to make the same outfit, but Jackie is 2.5 times bigger than Lizzie. Where will the ordered pairs representing Jackie's pattern be, assuming Lizzie's pattern is dilated? All right, so basically we are dilating this image by 2.5. And it does say that we are assuming that the pattern is dilated from the origin. So that's the rule that we used earlier. All right, xy becomes kx, comma, ky, where k is the scale factor. Now, do we know the scale factor in this one? All right, does it say how much bigger this triangle is becoming? All right, how, or not triangle, but how much bigger is it becoming? 2.5 times bigger. So this time we didn't have to solve for the scale factor, it tells us. So k is going to be equal to 2.5. It does want all of the ordered pairs. All right, so first we need to figure out what all the original ordered pairs are, and then apply that rule to each ordered pair to get the new image. So I know you'll probably need more than just this one slide to show your work, so the slide underneath it too is the same. All right, you can show your work there. But identify all your original coordinates. So we have P is -1, 3, right? And then P primed, we're gonna apply that rule. We're gonna do 2.5 times x, which is -1, and 2.5 times 3. And then simplify it we get negative 2.5 for p prime and 5. Or wait, 2.5 times 3 is 7.5, sorry. All right, and that's one of my answers. Do you want to see another one, or do you want to find the other ones by yourself? All right, we'll do one more together, and then you'll find the other ones by yourself. So just apply the same rule. We want to list what A was, which is 1, 3. Apply that rule to A prime. We're multiplying it by the scale factor for each one. All right, you might not have to show your work for this step if you are getting the point already. But A prime becomes 2.5, comma 7.5. All right, now find it for T, E, R, and N on your own paper. Maybe like a minute or two. If you look down on your notes, here's the answer. All right, so this is what it looks like once we plot all of those points. All we did was multiply 2.5, the scale factor times the x and y. All right. So now that we've done that, let's talk more about dilation relationships. We have, when a figure is dilated like the one below, notice that the shape remains the same even though the size is changing. So the triangle is still a triangle even though the size is changing. The triangles below are similar, meaning they are figures that have the same shape but not necessarily the same size. Remember, for two shapes to be similar, they need to have corresponding angles that are congruent and sides that are proportional. Every time a figure is dilated, the result is a similar figure. All right, so we kind of talked about that before, but here it is again. Similar shapes have the same angle measures, but different side lengths that are proportional to the original. Practice 1, so quadrilateral ABCD and its dilation, quadrilateral A prime and so on, are shown on the coordinate plane. In the center, if the center of dilation is at the origin, by what scale factor was ABC dilated? All right, so since it is dilated at the origin, write down the rule that we use. All right, so our original coordinate will be kx, comma ky, where k is our scale factor. It doesn't tell us what our scale factor is this time. That's what it's asking us, by what scale factor. So we're trying to find the value of k. But we do have both figures shown. So just take one or two of the points. So let's take point A. What is the coordinate for point A? 0, 3, good. And then what is A prime? 0, 9. So somewhere along the way, we multiplied it by k. We just need to figure what that is. So I have basically 0 times k equals 0, which won't really help us out because anything times 0 is 0. So k could be anything if we just use the x value. So try the y value. We multiply 3 by k to get 9. use your inverse operations. What's opposite of multiplying by 3? So we're going to divide by 3 on each side. And k is equal to what? K is equal to 3. Can I be done? Did we find the scale factor? Right, yes we did. We can just test out maybe another point just to be sure. That's what I would do on a test, is I test out maybe one more point. So let's try point C. What was point C originally? Four, -3, good. So 4, -3. And then C primed is 12, -9. Good. All right. So set up your little side algebra. So somewhere along the line, we multiplied 4 by k to get 12. Opposite of multiplying by 4 is dividing by 4. So k equals 3. Does that match up with what we found for point A? All right, yes. So we have the correct answer. All right, questions? Now I'll have you guys try this next one on your own. I think you guys are getting the pattern of it. So practice 2 says pentagon EFGHI is shown if it is dilated by a scale factor of 5/3 from the origin to create the dilated image. What is the ordered pair of point G? All right, so multiplying by a fraction, you can use your calculator, so I'm going to kind of let you deal with that. It gives you the scale factor. So what is going to be the new point G? I'll give you about a minute. So for this one, let's see if you got a good start. It's only asking about the point G. So I'm going to first figure out what the original point G was. What's the original point G? 3, 6. And I'm going to apply that rule. That rule I'll write up here. All right, we multiply the x value and the y value by k, our scale factor. Did it tell us what the scale factor is? Yes, it explicitly says it right here. Didn't mean to cross it out, sorry. All right, but it explicitly says it right here. So I'm going to put 5/3 times my x value, comma 5/3 times my y value. Now, if you're good at fractions, great. If you're not, you can just enter this in your calculator. You can put the fraction in parentheses like this. So it'll actually look more like this in your calculator. 5 division sign 3, close parenthesis, and then times 3. What value did you get for x? You should have gotten 5, right? Then do the same for the other one. Do 5/3 in your calculator times 6. Put it in parentheses so that it reads it the right way. And if you put it in the right way, what did you get for your new y value? Right, you get 10. So G prime is at the point 5, 10. All right, good. Any questions? All right, then moving right along. We have a U try on the next one, so practice 3. Same thing, we are dilating by a scale factor of 1/4 from the origin. So what is going to be the ordered pair of L? So we do about a minute